You know, have you ever thought about chemistry as, well, as a kind of architecture? Where instead of building with bricks and steel, you're building with atoms and bonds? Turns out every single organic molecule, from the simplest fuel to the most complex medicine, actually has a blueprint. And in the next few minutes, we're going to learn how to read those blueprints together. So here's the thing about organic chemistry. The biggest challenge is just the sheer scale of it all. We're not talking about a few dozen compounds, we're talking about a library with, in theory, an infinite number of books. So how on earth do you organize an infinite library? Well, you need a master map.
And yeah, this image really drives that point home, doesn't it? At first glance, it just looks like chaos, a total starburst of complexity. Trying to memorize all of this would be absolutely impossible. But here's the secret. It's not about memorization, it's about classification. We just need to find the address for each molecule on this master map, and that always starts with its fundamental skeleton.
All right, so where do we even begin this architectural journey? Simple. We start with the foundation. Every single organic structure starts with one fundamental choice in its carbon framework. Is it going to be an open chain, or is it going to be a closed ring? And this illustrates that first big decision perfectly. Over on the left, you have acyclic compounds. Think of them like open roads. The chain of carbon atoms has a clear beginning and a clear end. On the right, you've got the cyclic compounds, where the ends of that road loop back and connect, forming a closed ring. This single choice, open or closed, is the first major fork in the road in our architectural blueprint. So let's focus on those open chains for a second. The official term is acyclic, which literally just means not a cycle. You'll also hear them called aliphatic compounds. But the crucial point to remember is that their carbon skeleton is a line, not a loop. Simple as that. Now, even these open chains aren't all the same. It might be a simple straight line of carbons like we see in ethane, or it can have branches coming off the main path like in isobutane. Now, the note on the right is key here. The term open chain only refers to the carbon skeleton. Other atoms can and very often do attach to that chain, but we'll get to that in just a bit. All right, so we've covered the open planes of acyclic compounds. Now let's explore the world of closed structures, the rings. And trust me, this is where the molecular architecture gets really interesting.
So, once we've decided our blueprint is going to include a ring, we hit another architectural fork in the road. This time, it all comes down to how the atoms inside that ring behave and bond with each other. This decision splits all cyclic compounds into two major categories, alicyclic and aromatic.
So what's the real difference between them? Well, think of alicyclic rings as just open chains that have been bent into a loop. Chemically, they behave in a very similar way. Aromatic rings, however, are special. They have a unique, flat structure with a circle of electrons that are shared across the entire ring. This whole arrangement makes them incredibly stable and gives them a completely different set of chemical properties.
Okay, before we go any further, we need to define a key term, because it's crucial for the next step. The word is heteroatom. Hetero just means different, so a heteroatom is any atom in the carbon ring that isn't carbon. Most of the time, you'll see oxygen, nitrogen, or sulfur just swapping places with a carbon to become part of the ring itself. Keep this one in mind.
And this concept of the heteroatom allows us to add another whole layer to our blueprint. If a ring is made only of carbon atoms, we call it homocyclic, homo meaning the same. But if just one of those carbons is replaced by a different atom, like that oxygen you see right here in tetrahydrofuran, the ring suddenly becomes heterocyclic. This ring diagnostic matrix is the perfect little cheat sheet for putting it all together. To classify any ring, you just have to ask two simple questions. First, what's its behavior? Is it alicyclic or aromatic? And second, what's its composition? Is it homocyclic or heterocyclic? This gives us four neat quadrants. For example, benzene is aromatic and it's made only of carbon, so it's a homocyclic aromatic. Tetrahydrofuran behaves like a chain, but has an oxygen in the ring, making it a heterocyclic alicyclic. It's a beautifully simple and powerful system. So far, we've only talked about the foundational skeleton of the molecule. But what about what gives a molecule its unique personality? Its color, its smell, its reactivity. For that, we need to add a little flair. And this is exactly where functional groups come in. I love this analogy of modular accessories. The carbon skeleton, which is represented by that R in the box, is our universal base. It could be any chain or ring we've discussed. The functional groups are like different attachments that you just snap onto that base. An OH group, for example, makes it an alcohol. A COOH group makes it an acid. These accessories are what truly define the molecule's final character and function.
Okay, so we've got our two main concepts, the foundational skeleton and the modular accessories. Now let's combine them to see the full picture and understand the complete identity of any organic compound.
You know, it all just boils down to a simple two-step process. First, you identify the skeleton. Is it an open chain, a heterocyclic aromatic ring? That's your foundation. And second, you add the accessories. What functional groups are attached to it to give it that specific character?
And this slide puts it all together beautifully. Look at the molecule on the right. A moment ago, this might have looked totally intimidating, but now we can read its blueprint. We can see the core skeleton, a ring containing a nitrogen heteroatom, and we can see the accessory, a functional group attached to it that dictates its unique properties. The final identity is always a combination of the skeleton and its accessories.
So there you have it. We've gone from what looked like molecular chaos to a clear architectural system. We've learned that every organic compound is just a combination of a foundational skeleton and some modular accessories. You now have the key to reading the blueprint of nearly any organic molecule. So the only question left is, what could you build?